Welcome to Prime Time in the BU Library. Prime Time is designed to celebrate the experiences and accomplishments of Bethel faculty, students, and staff. It is a collaborative project between the Friends of the BU Library, faculty development, and other offices on campus. We record most of our programming, and you can find recordings in the BU Digital Library. An announcement on Tuesday, October 18th, Tandon Brecky, Assistant Director of Community Engagement and Service Learning, seniors Jolene Rodick and Kirsty Finau, Dr. Harley Schreck, Professor of Anthropology, and two representatives from the Urban Farm and Garden Alliance share about their community university partnership and how it's benefit all involved. Today, Edgren Scholars, Dr. Brian Turnquist, Professor of Math and Computer Science, seniors Annie Melling and Peter Klemme will share the statistical tool that they developed to explore the connection between the sensations of pain and itch. Join me as we welcome you.
Well, thank you all for coming. Great to have a few of my students here. I know whenever there's a math talk advertised, most people look at that and just think I'm not going to that. And also I know Dr. Johnson invited his students also, so welcome to you as well, and all interested parties. This is a talk about our summer research, but it's also about a broader area of research that's going on internationally. So the research goals here for this area are to understand the physiological basis of pain, itch, and to develop treatments for chronic pain and chronic itch. So if you've ever known anybody who has chronic pain or chronic itch, it's a very serious medical problem that has a lot of side effects besides just the discomfort from ongoing pain. It makes it difficult to sleep at night. And when you sleep, your mind isn't right and causes tension in your family, and people get divorced, and so it's a serious medical problem that has a lot of implications. And of course, anytime you pop a couple Tylenol, you are pouring funds into the ongoing effort to understand and treat pain. And of course, you've got a number of creams that have been developed. Those are used for itch. Eczema is a serious medical problem as well that causes chronic itch. So that's all to say we're glad to be a small part of this ongoing effort to develop treatments for this serious problem. This is our part of it is part of an international collaboration. So just some of our colleagues here just mentioned quickly Barbara Namer at the University of Erlangen. So in their group, they do what's called Micro Biography with humans, and that's a very interesting process. So you have an awake human subject, and you insert electrodes through the skin into a nerve bundle, and then stimulate the peripheral nervous system. You can then record the electrical signals, and you can also interview the subject while that signal is being received and say, hey, how does that feel? Does that feel itchy, or does that, how would you rate your pain on a scale of 1 to 10? So it gives us the opportunity to correlate the effective sensation that's coming in the central nervous system with the peripheral signals that are coming in through our electrodes. And it's, to get those electrodes in there is a bit of an art, and so there's only about 3 people in the world who know how to do this, and Barbara's one of them. And of course, they all learn on themselves and on each other and on other people who happen to be in the laboratory at the time, the volunteers, as we call them. So a couple other important people in the group, Matthias and Martin, are doing animal electrophysiology, and so in that we're also inserting electrodes into nerve bundles. That's done with the animals anesthetized and through a surgical procedure. And so that's also a very specialized kind of thing. And as a mathematician, it's very interesting to me to be around the surgery that's being done and to see that firsthand. And when alarms go off, I go find somebody to help because I don't know what to do if the oxygen sensor is telling us that the animal's waking up. Another person who helps out is Bob Lamont at Yale University. He does human psychophysics, so that's, again, having awake human subjects being interviewed about the response to, let's say, an injection of an itchy stimulus or the application of a burn or painful stimulus, and then they rate their pain over time. So Bob does a lot of human psychophysics, also does a lot of research in rats. The main animals that we're using are rats, monkeys, and pigs. Ellen Jorum at University of Oslo is part of our human clinical trials, and she sort of manages a huge pain clinic there. And so in that case, we're bringing in people who have chronic pain or people who have chronic itch, and we're trying some of these measurement techniques and therapies to see if they get relief. And typically, it's one thing to try an experimental procedure on a graduate student who's healthy. It's another thing to have a person who's suffered for 10 years with chronic pain come in, and you're sort of trying to very gingerly do these procedures to them. And but it's good because then we're kind of reminded and grounded in why the research is important when we meet these people. Okay, so just to give a little background before Annie and Peter come up to talk. So I mentioned the insertion of the electrodes. Once those are inserted into the nerve bundles, we can record. These are action potentials, so the neuron will fire in response to certain kind of stimuli. It won't fire in response to other kinds of stimuli. So we have some neurons that are only cold receptive or only heat receptive, or they're receptive to touch. There's some that are receptive to touch, but that aren't receptive to pain. So we have sort of a classification that's going on during the searching process for a neuron that we can record. And once we found the neuron, what we hope is that we can get a signal coming just from one neuron. Sometimes it's two, but ideally just one neuron in our studies. And so each one of these spikes indicates that the neuron has fired. And so we discriminate these, and we through a computer analysis program that I developed, we isolate these and turn those into just single timestamps. And then we measure the distance between those timestamps. Well, we do a lot of things with them, but for the purposes today, we'll just talk about the distances between these. And so, for example, between this spike and this spike, we have 91 milliseconds. And if all the spikes were firing at 91 milliseconds, that would be 11 hertz, or an 11 hertz signal, which is a very, very low tone. But they aren't, so what we do is we assign the 11 hertz signal to just this one spike, and this is called instantaneous frequency. There's kind of a contradiction in terms, right? Because frequency is an ongoing thing, but we call it instantaneous frequency to indicate how close this spike is to its neighbor. And so once we've got those measurements, we convert those to frequencies, and then we can plot those in time here. So this is 102 seconds, 102.4 seconds here, and we see these three spikes right here. The distance between this one and this one is small enough that that corresponds to 140 hertz. This down here, well, here's this one here, the 91 milliseconds, that corresponds to 11 hertz. We can see on the scale over here that's roughly about 11. So as you look at one of these frequency plots, you can see from the height when the spikes are firing quickly and when they're firing slowly. All right, so here's some sample stimuli and some neural responses that we've recorded in the laboratory. These are in response to painful stimuli. These are in response to itchy stimuli. And I'll just play these for you so you can hear what it sounds like in the laboratory. So here's the first one. and I'll play it at the speed that would actually be heard in the laboratory first, and then I'll increase the time, the playback speed a little bit so we can hear more details. So when I press play here, what you'll hear is the high frequency entrance around 100 hertz, and then we get down here to 1 hertz. So 1 hertz is about 1 beat per second, right? So you'll hear that 1 beat per second, and that'll go on for a little while, and then I'll go back and speed it up so we can hear the whole thing. We don't want to sit here for 2 minutes. Okay, here we go. Oops. Try it again. This is what experimenters are hearing in the laboratory when they're doing the recordings from a nerve bundle. And let me just play this a little faster now so we can hear the second part of it. So I'll play it 10 times faster, and what you'll hear is once we get out to here, you'll hear this, these pairs or these little bursts that come in. This is the response that we're looking at here to a 49 °C laser burn. And so this is over 2 minutes, and here's the initial onset of the stimulus here. The nerve starts firing a regular pattern, and then after about 40 seconds starts this double. It's a little hard to hear. There's two very close together, but it sounds kind of like one. Let's listen to it one more time. Okay, that's one example. Here's another stimulus. This is an injection of capsaicin. So I know this is this is histamine. So histamine is an extremely itchy substance, and when you inject it under your skin, it just itches like crazy. So this is what it sounds like, and I'll play it at high speed here. Okay, you get the idea. Here's one more. This is an application, what's called cowhage. Cowhage is a plant that's native to India, and what you will, if you look at cowhage under a microscope, you see that on the end of it, it's like, have you ever gotten burrs caught in your socks, or it's like it's got tiny little, they're not hooks, they're little syringes on the end of it, and so the Lord had some idea of wanting to have a plant on the earth that would inject your skin with this substance, and thousands of teeny little injections. We found it's quite useful as an itch stimulus. So we'll apply the cowhage to the receptive field, and this is what it sounds like. So you can see that for an experimenter who's in the laboratory, when they've done 100 experiments or 200 experiments, they get an idea. These experiments take all day. And so you get an idea, okay, there's something going on here. There's something about the pattern that's characteristic of the sensation. It's not as simple as I'm presenting here. There's a lot of sort of gradations in between. And I think we would also agree that, when you're, sometimes you can experience itch and pain at the same time. Or sometimes if you have an itch, what do? You scratch it, okay? Which in a sense can produce a painful sensation, and maybe that disrupts the itch signals. But it's not as straightforward as just saying, oh, is it this or is it this? This is the injection right here of capsaicin. Capsaicin is the hot substance in hot peppers, And when you inject that under your skin, that is extremely painful. Anybody that we inject this with, that's sort of our reference for painful, like a 10 on the pain scale. Right? You inject it under their skin and they're like, okay, that's a 10. Or they can't say anything at all. And so then you know you've got the right stimulus if you want sort of universal agreement of this is what pain is, in case you were wondering. And so this is a typical discharge from a capsaicin injection. We see a burst here right at the injection, and then it's odd because it goes silent for a significant period of time, and then it comes on again. This is after almost 2 minutes. It comes on again, just all of a sudden, all at once. Brrr. We don't know why. Okay, so we're studying the patterns of neural responses in response to various kinds of stimuli. I just want to pause for a moment before Annie comes up and see if there's any questions on the introduction here. Yep, Joe?
So these are this is when the neurons are firing. Does this directly relate to how a person is experiencing a sensation? Like when there's a burst, is that another feeling of pain?
That is a very good question that we don't have a good answer to yet. One of the problems we have is that in order to get a single fiber recording like this, it pretty much has to be done on an anesthetized animal. And so we're actually, we just got awarded an NIH grant for 5 years to answer that very question. Right? These are called translational studies. Translational studies are where you try to understand what's going on physiologically in the animal and then translate that to what it would be for a human. And of course, pain can be based on a lot of things. Right? If you're distracted or if you're having a good day, maybe you can withstand the pain a little more than other days and you might rate it lower. So the affective part of it, the psychological part is important.
Most receptors are different receptors for different stimuli, like warm, cold, pain, touch, pressure. What about itch and pain? Are they separate, or are they different responses from a single receptor?
Yeah, that's the question we're trying to answer. And that's, I'll talk a little more at the end about some of the future directions, but that very question is what this is all about. Okay, Ian? I go ahead and another slide. Oh, yeah, so then our specific goal, in case you haven't figured it out, is to develop a statistical measurement that characterizes the pattern of neural discharges in the peripheral nervous system. I'm so glad my students are here because they always keep me, sort of on track in my lectures. Otherwise, I'd be talking all kind of crazy stuff. So thanks for being here, you guys. And let's have Annie come up and talk a little bit about the research itself.
So in order to understand the method that we developed a little bit better, I'm going to go over some of the foundational mathematical knowledge that you need to have in order to kind of understand where we were going with it. So we started with a method developed by Kanioki and VTech to divide up a time series into specific frames. So we see on the top here, we have a time series. Each of these represents a timestamp, these lines. And what we do is we determine, or we choose our frame size feed. And then what we do is we go through the time series and we divide it up into little segments, each of with feed. And we count the number of timestamps that fall into each frame. So for this first one here, there's 4 lines, and so we say that there are 4 events in that frame. And then we go across all of the frames and we count the number of events in each of the frames. And from there we can create this density histogram where we see the percentage of frames that contain each number of spikes. So for example, we see that there are 3 out of the 9 frames contain 2 spikes in their frame. So a previous method that was developed by LeVar that we kind of started our research with looking at went off this density histogram and went off a set frame size of the mean ISI, or the mean interspike interval, and then matched up or kind of fit the distribution with either a normal or a Poisson distribution. And from there characterized it as either regular, irregular, or bursting. So fit into those 3 distinct categories. And one of the things that we wanted to expand on this method was looking for kind of a spectrum of values. So we wanted to have a spectrum ranging from regular to bursting, where we could have intermediate discharges that had some sort of intermediate behavior. So what we developed was a measure called the density product, and this is our novel approach to spike train classification. It involves 4 parameters. We have our phi that I discussed in the previous slide, so our frame size. We also have our d sub 0 phi, which is the percentage of frames that have no spikes in them. Our d sub 1 of phi, the percentage of frames that have 1 spike. And our d sub 2 plus of phi that has the percentage of frames with 2 or more spikes. So our goal here is to maximize the number of frames that have either 0 or 2 spikes, with the goal of looking for characterizing or identifying that bursting behavior, and minimizing the number of frames that have just 1 spike. So that is reflected in our equation here. So the first part of this, I'll talk about the 4 in a second, but we have our d sub 0 phi times 1 minus d sub 1 of phi times 2 of d sub 2 plus of phi. So again, our d sub 0 and our d sub 2 plus are being maximized, and our d sub 1 is being minimized. So we calculated that the maximum value for this expression right here would be 0.25. And so we decided to multiply this by 4 in order to obtain our classification on a scale from 0 to 1. Then we define the maximum density product as the maximum value that this density product can obtain for a specific value of phi by iterating through all potential values of phi and then taking the maximum value that we obtained from there. And we called this the maximum density product. And this became our classification measure. So just to give some examples of what this looks like, here we see a very regular discharge, consistent spacing between our timestamps, and this results in a very high percentage of frames that contain just 1 spike, and a very low percentage that contains 0 or 2 or more spikes. This results in a density product that is very close to 0, so very in that regular region at 0.014. Next we see an irregular discharge, less consistent behavior, and the percentage of frames that have 0, 1, or 2 or more spikes, they're a lot more consistent than with the regular behavior. And this results in a density product, a maximum density product, at 0.32. So somewhere in between that 0 to 1 range, somewhere in the middle. Lastly, we see our bursting discharge. This is very purely bursting. And so we see that the percentage of frames that have 0 spikes and the percentage of frames that have 2 or more spikes are maxed out at 0.5 each, which results in our maximum density product of 1, the maximum value that we can obtain for this measure. So what we're left with is this continuum, and it's a continuum from regular to bursting. Initially, we weren't quite sure where to draw the line between this regular and the irregular region, and between the irregular and the bursting region. So that is where we, next, I'll talk about how we developed what those are, but the general idea here is that we have this continuum that we can classify discharges with. So in order to figure out the theoretical lower bound of our irregular region, we identified that a purely irregular discharge is going to be approximated by a Poisson process. So we can use the probability density function for a Poisson distribution, the formula is given here, for finding that probability of having n spikes within a frame. So using this equation right here, we then said that our d sub n of phi is going to equal f of n for all n greater than or equal to 0. Then we identified that our d sub 2 plus of phi is going to equal 1 minus the d sub 0 phi plus the d sub 1 of phi. So given those two facts right here, we then could take our density product equation with our phi as input and plug in our f of n, or our d sub n of phi, for each of the 3 values and obtain this equation right here. We are then able to maximize this function relative to phi in order to obtain our theoretical maximum density product for our purely irregular discharge at 0.2636. And we identified this and called this term our I star. Next, we needed to identify where the upper bound of the irregular region was. So one thing we observed was that the length of the discharge did impact the maximum density product that we obtained. So a much shorter discharge was obtaining a different maximum density product than when you have a much larger discharge, even if they're both bursting behavior. So we identified that we needed to base this upper bound based on the length. We called it UB of L. And the general idea here is over here on the right, we see what we did was we created 1,000 artificial discharges that were all irregular. And we created them with length 50, and we did the same for 1,000 bursting discharges. And then these right here are the distributions of the maximum density products across all 1,000 discharges. And we identified our UB for length 50 as the point at which the right and the left tails of these two distributions intersect. We did the same thing for length of 100 here. We see that the maximum density product, the place where they intersect, that upper bound value, is a little bit lower down here. And one thing that we observed was that as the discharge length increased, that spread, that distribution here, the width of that, decreased down towards our I star value for our irregular discharges as the length increased. So we were able to calculate this upper bound value, finding that intersection of the two tails, for 6 values, and then interpolated these 6 values to create this function right here to calculate our upper bound value for any value of L greater than or equal to 25. 25 we just identified as needing to have a significant length in order to calculate this upper bound. We need to have enough points in our data set. So now we have our spectrum filled in a little bit more. We see that discharge with maximum density product between 0 and 0.26 is going to be classified as regular. Between 0.26 and our upper bound, calculated based on the length, will be an irregular discharge. And between our upper bound and 1 is going to be our bursting discharge. So we were then able to apply this technique to many, many data sets. These are a few that we looked at. We see in this first one here a regular discharge that produced a maximum density product of 0.3 or 0.3, so closer down to 1 on that, or closer down to 0 on that spectrum. Then for this irregular discharge right here, we see the maximum density product was 0.448, so in the middle of that spectrum, past the 0.26, but below that upper bound value still. And then bursting, this discharge right here, we see the maximum density product is 1. One of the other results of our research this summer is that we developed a segmentation technique in order to take a discharge that had multiple different types of behaviors and to segment that into separate pieces and then calculate the maximum density product for each segment. So up in the top here we see this discharge starts off with some irregular behavior and then follows with some bursting behavior. You see the density product values here indicate those. Second one here, we see we start off with some bursting and then go down to a more regular segment of the discharge. Another result of this segmentation technique was that it did pick up on changes within a specific region. So we may have bursting, but we may have different types of bursting. So this discharge down here has, it's all classified as bursting, but we have 3 different degrees of bursting. So that was another thing that we were able to look at a lot. And as you can imagine, with all of these density product calculations, it took a lot of computations. In order to calculate one maximum density product, you need to iterate through all the potential frame sizes between the minimum and the maximum ISI. So that was a lot of computations. Initially, we started out with that in Mathematica, but then Peter ended up playing a very crucial role in our research this summer in that he was able to help us compute these computations a little bit faster, and he'll talk a little bit more about that. But Peter was very instrumental in helping our research go a lot farther this summer. So, Peter?
Well, thank you, Annie. Thank you, Andy, again. So as Andy mentioned, Mathematica really it took a long time to get all of the computations run, and because the maxDP function really just has lots of calculations involved with it, and especially when, as Andy mentioned, the segmentation, sometimes the maxDP had to have been run several thousand times, and it could take up to 4 days to run full segmentation algorithms. So Mathematica was good as a prototype, just to make sure that the actual algorithm worked. However, just after a while, we needed to go into C++ programs. So with that, I'm going to do the demonstration in Mathematica. So here what I'm doing is I'm just generating a set of 5,000 points of the time series to simulate the neural discharges. And then we are going to run maxDP algorithm as written in Mathematica and see how long it takes. Yep, so as you can see, it took 4 seconds there. And although 4 seconds really isn't that bad, if you just do it once, if you're running thousands of times, it can become just detrimental to research and can just eat up a lot of time. So this is going to run the algorithm in equivalent program written in C++. So you can see how long it takes here. As you can see, there's a major factor of difference. It once took 4 seconds, now it just took less than 1 second. And so, further explain what exactly is happening here. So, just to be clear, that second faster program is not written in Mathematica. All Mathematica is doing is it's sending the time series over to the Linux server, and then on the Linux server, the C++ program is run, to which then the output is sent back to Mathematica. So all Mathematica is doing is sending and receiving. It's not actually doing the computations. Just to be clear about that. And so here is a time comparison of this. So as you can see, with larger data sets, Mathematica really just starts taking up lots of time, especially when it's 10 seconds times 1,000, where now all of a sudden you've got several days to run these computations. And so running it in C++ just made it a lot faster. And yeah, so I want to go a bit into why C++ is faster. Main reason really is just that C++ is compiled and Mathematica is interpreted, and I'll spare you the details on that, but you just need to trust me that it's faster. And so even though you have to send all the data to Linux server for C++ to be run, it still ends up saving lots of time. And so in the end, however, Mathematica was useful for creating a prototype, just creating the algorithm. It's easier to write in Mathematica than in language like C++. However, when we were when we were working on larger amounts of data, then compiled language such as C++ was necessary. And so with that, I'm going to turn it over to Dr. Turnquist to talk about the future of this project.
So just kind of current and future, and then just open it up for questions. So we have a manuscript that we submitted to the Journal of Neuroscience Methods, and got it back with reviewer comments, so we're currently addressing those, and hopefully we'll get the paper published in January sometime. And Annie's the first author on that paper. Develop techniques to modulate itch sensation. I'll be out at Johns Hopkins next week, and one of the things we're currently working on is So if you have an itch sensation, is there a way to modulate that into pain and then modulate it back into itch again? And of course, you could stick the person with a pin and that would turn itch into pain. But what we're trying to do is see if we can do it through a non-painful stimulus. So for example, can you have an itch sensation and can we provide a heat stimulus that's not painful normally, but that because the itch is already there, that we modulate that into a painful sensation. And then when you turn the heat off, see if it can go back to itch again. So that's a fundamental question that we'll be working on. Another one is kind of as a side project on this, we worked on generating these artificial data sets, which gave us the opportunity to really be able to create a continuum of sort of perfectly regular, perfectly irregular, perfectly bursting in a sort of mathematical way, and to control all the different sort of subcategories and in-between areas that there are. And so another thing we'll be doing next week is just trying to artificially stimulate electrically and see if subjects can detect, for the same stimulus frequency, a change in the pattern. Right? And if they can detect the change in the pattern, whether they just detect it even as itchy or painful, in a sense, even that is a significant indication that pattern itself is an important component of sensation. So those are two things we're currently working on. I'm also working on some stuff Peter was doing at the end of the summer, better characterization of bursting, which has a lot of different flavors to it. So that's kind of the current and future directions we have, and I just want to open it up for questions for any three of us. Why don't you guys come on up?
Yeah, I have two actually. So in either the departments, pain or itch, through all your testing of different stimuli, the peppers and laser burns, did you see more similarities or more kind of colorful spectrums in the results?
I think you do see the differences in there, and they are significant enough differences that you're sort of left with the impression there's got to be something here that's important. But it's not so simple that it's been discovered 30 years ago. So I think we're kind of at the place now where we have the right team of collaborators, we have the right techniques that we're using to finally come up with an answer.
I have a biology question. So let's assume now we have a receptor for itch, which can be stimulated to also produce pain. Now, are we going to open the door to other receptors, like warm? Because when you get warm close to tissue destruction level, now it gives you pain, or cold, or pressure. So is this opening a door that historically we always thought one receptor, one sensation? Now this will be really different if one receptor can give two sensations and pain is one of them.
Yeah, exactly.
So are you going to spread into
Yeah.
something like that?
Yep, that's exactly right. That is the dominant theory. And so the pattern theory is, I think in the people that I know, they do believe that the pattern is significant. Yeah, even though historically it's been understood that there's sort of different populations for every different sensation. So, yeah.
I have a math technical question for you guys. Okay, so your upper limit for your yes, there we go. Your upper bound. You use the number of spikes. Does that mean the length of discharge? So does that mean that this is going to be really dependent on the average spiking rate of the neuron? And how, or is this actually, in the way that you've taken and done the interpolation, does that actually manage to make it stable across neurons that discharge at different average rates?
So
Sorry.
So one of the nice things about the density product is that it's invariant for frequency. So it just measures pattern, only pattern. And so frequency is a separate axis. And so you can really combine the two measurements together. But a second answer to your question is that if you think about 10 spikes, it's pretty hard to say what your pattern is after 10 spikes. So it's just the old question of statistical significance. What is the n that I need in order to make the right decision about what this is? And I think that so this is a classical statistical technique, and I've thought whether a Bayesian technique might be more powerful in this example. What do you think?
I have lots of thoughts.
He's our local advocate for Bayesian statistics, so we don't talk to him. Other questions?
Has there ever been a reversal of the process? So instead of kind of obtaining the firing data, sending the firing data through the neuron and asking to kind of interview?
That's what we're hoping to do next week. Yeah, we'll do it using artificial discharges. But what you could do is we could actually use one of these recorded discharges and just play that back through the peripheral nervous system and see what happens. Okay. All right.